us how the connection between Liz's global problem solving class and your systems thinking theory came to be?
In 1992, when I was in graduate school, I learned about systems thinking from my advisor in grad school. She gave me a copy of a book called The Fifth Discipline, which was written by Peter Senge, who's an MIT business person and one of the leading experts in the world on systems thinking. And that book changed my perspective on how I think about organizations and the environment, because systems thinking is kind of something that can describe lots of larger, complex structures. And so when I started to share those ideas with Liz, she said, "Wow, this is a great idea. We might be able to use that in our human rights courses and possibly some other social studies classes." And the more you learn about systems thinking, the more you realize you don't want to just focus on events and patterns when you try to solve problems. You want to look at the system that the problem is embedded in and look at leverage points in the system to nudge the problem or the challenge in the right direction. Because systems are very resistant to change. You nudge it from one side and the other side pokes back. And so you have to be aware of the dynamics of the system and how things interact within the system to try to get the leverage right to make changes that you'd like to have.
What exactly is systems thinking?
So let me give you an example that illustrates systems thinking. One of the examples we use in the global problem solving class is we start off with a description of Easter Island, which is in the South Pacific. And we describe one of the systems patterns. Now there's one of the names of these patterns is archetype. We see often archetypes in, say, psychology. You might have the archetype of the hero, which is common to a culture. But in systems thinking, there are specific patterns that are common to all systems. And one of them is called the tragedy of the commons. And the example that we use is Easter Island. But let me give you a simpler example to illustrate what we mean by system. The tragedy of the commons refers to, in England, they often called parks commons. As a matter of fact, I lived in Cambridge, England for a while, and I lived right next to Midsummer Commons, which was a huge park. The commons used to be grazing areas where they would graze cattle, and the cattle would go out and graze. And so here's the systems idea. You have a village with a large park, or a commons, and every person living around that commons has a few cows. And they put cows out to graze on the commons. They consume a common resource, which would be grass. Now I'm Mr. Jones, and I realize, hey, my neighbor, Mr. Smith, has put 2 of his cows out. I only have 1 cow out, so I'm going to throw a second cow onto the commons. And pretty soon other people start to see that, and they do it. And pretty soon what happens? We throw so many cows on the commons that the system collapses. That's called the tragedy of the commons. When you have individuals acting in their own best self-interest, not looking at the system they're in, and the fact that they need to regulate what they do if they want the system to survive. That's an example of, when we talk about systemic thinking, that's the type of thinking that we need to do more of, because if we want to create the futures that we want to have, and we want to have the environment that we want to have, in my opinion, we need to think systemically about those types of things.
How does systems thinking help students identify solutions to problems?
So one of the things that we do is we have the kids draw diagrams. We call them systems diagrams. And the nice thing about drawing a systems diagram is that there's no right answer. We give the students large sheets of newsprint and magic markers, and we describe the 3 components of a systems diagram. And the 3 components are very simple. One is positive feedback loops. Now, positive feedback loops don't mean that they're good. They simply mean reinforcing feedback loops. Things that we have a snowball effect, or you have a classic example would be a run on a bank, or when things accelerate quickly in a given direction. We call them vicious cycles or virtuous cycles. That's a positive feedback loop. And you could draw on a piece of newsprint the connections between events and the positive feedback loops that occur between the connections that are within a system. So we have kids draw positive feedback loops on their systems diagram. We also have them draw what we call negative feedback loops. Negative feedback loops aren't bad. They're not negative. Negative feedback loops are things that negate change. They prevent change from occurring. And that often happens in systems. You have things that are interacting against each other to prevent change from happening. So we show them how to draw negative feedback loops. Then the last component of a systems diagram is the fact that there's often delays between cause and effect. You can do something at a given point in time. The effect of that isn't really conceived or isn't realized until a few days later, a few years later, and maybe at even a different location. So what we do is we have the students, let's say, pick a global problem. It could be homelessness. And we have them list 8 to 15 variables that affect homelessness. And then they take a piece of newsprint and they put those variables on the newsprint, they try to connect them with arrows and diagrams and loops to show both negative feedback loops, positive feedback loops, and delays between cause and effect. Now the cool thing about this is there's no right answer. So you could have two groups or three groups, using the same variables, and they might draw very different systems diagrams, but at least that gives them a picture of the system that they're working with. It also gives you, the key thing is, it gives you potential leverage points. Where do you get into the system to impact what's happening? And that's what we try to train the kids to do, is take a look at the system from a diagram's perspective and then look for leverage points in the diagram.
Cut.